Hello Math 8 students, this is Open Up Resources, Unit 2, Lesson 7, Similar Polygons. To get started, because it's been a long time since we've come back from winter break and dealt with this, what is similarity? In the mathematical sense, I asked you to review your Lesson 6, specifically the Lesson 6 summary, to help you answer this. And as I write this down here, since I only have 2 hands up, everybody else who doesn't know should probably write the answer right here. What is similarity in the mathematical sense? Emily. Holy cow, that sounds like you read it directly from Lesson 6. If only everyone else could look up Lesson 6 and have found the answer just as well as you. Great job, Emily. 2 figures. It's even highlighted for you, isn't it? Yup. 2 figures are similar if one can be obtained from the other. Are we writing this down since I only had 3 hands that were up? Yes, and where are we writing it? Right here on Lesson 7, which has been passed out to you. 2 figures are similar if one can be obtained from the other. Through a series of, or I guess a sequence of is probably what it says. We'll go with sequence of. Translations. Reflections. Rotations. And dilations. Now, here's your challenge question, because we have to go back even further in our lessons to find this. What is the definition of congruence? I've drilled it into your head so much that I hope you don't have to go and look it up. Discuss with those around you. What is the definition of congruence? Let's just go a quick 30-second discussion here. Go. A billion times we wrote it down, yeah. Time's up. What is the definition of congruence? One hand ready to pass this term. Landis. That's not the definition. It's a characteristic, but it's not the definition. That's a characteristic, but not a definition. I'm not going to call on Emily again for this one. Let's try Garrett, see what Garrett knows. Definitely not anything to do with vertical angles. It does have to do with rigid transformations. Let's write this one down too, folks. 2 figures are congruent if one can be obtained from the other. Wait, this feels really familiar. Through a sequence. What? This is almost identical, isn't it? Of translations, reflections, and or rotations. Which reminds me that I do actually need to fix this here and make it an and or. Oh my gosh, they're almost the same? They are similar. What is different? Please focus on the differences here. Find it. We wrote it all down. I should see more than one hand up. Read through it again. What's the difference between these two definitions? I'll wait until there's more hands. Maddie, what's the difference? That is one of them, yes, because we are defining different words. Now that we've identified that this is the definition for similar and this is the definition for congruent, what is the actual difference between them, Audrey? One has dilations and the other doesn't. What do I call translations, reflections, and rotations? I summarized all of that with fewer words before. What did I call those, Callista? Rigid transformations. So again, let's talk about those differences then. If translations, reflections, rotations are rigid transformations, and they're basically the same except for this one has dilations, are similar figures going to be congruent? Look at the differences. They can? Okay, now it's time for you to discuss that. We're actually moving on to the lesson. Please ignore this. This comes later. There's nothing right now. If two figures are congruent, then they are similar. You need to identify, is that true in all cases, meaning always true? True in some cases, meaning sometimes true? Or true in no cases, meaning never true? We wrote down the definition of similar. We wrote down the definition of congruence. Now you need to decide, if two figures are congruent, then they are similar. Always, sometimes, never. 30-second discussion. Go. Okay, time's up. I want to hear from some students. What do you think? Is it always true, sometimes true, or never true? I need more hands. I gave you time to discuss. I would like some more hands. Xander, get us started. Explain. Okay. Let's go to Garrett, see if Garrett can add to that. Why? Okay. If they're congruent, they're more of the same, so they wouldn't be able to be similar because they're too much the same. Okay. What other thoughts do you have? Let's see who agrees and who disagrees. Raise your hand if you say it's always true, true in all cases. Raise your hand. Just one student. Raise your hand if you say it's sometimes true, or true in some cases. And raise your hand if you say it's never true. No cases is it true. Audrey's the only one who's correct. Well done, Audrey. Okay. Settle down. Voice is off. If figures are congruent, eyes on the screen. If figures are congruent, then one can be obtained through the other through a sequence of translations, reflections, and rotations. I said and or rotations. If they're similar, remember how everything is almost exactly the same except for we added one word and we said and or dilations? So if it's congruent, that means I can do a translation, a reflection, or a rotation, right? If it's similar, that means I can do a translation, a reflection, or a rotation. Oh yeah, we can also do dilations. So if two figures are congruent, then they are similar. This is always true. No idea why it's randomly changing to black there. It was pretty cool. Always true. So again, pay attention. Similar, that means we can do the rigid transformations, therefore it would be congruent, but we also allow dilations too. However, if it's congruent, that means only rigid transformations are allowed. So again, kind of think about what this means. Exactly, rigid transformations are an option. Do we have more options with similarity? Yes. But if all we're allowing is rigid transformations, then of course, in the one that allows rigid transformations, it's always going to work out. But let's go backwards now. If two figures are similar, so again, that's me taking this, rigid transformations and dilations allowed, or congruent, oops, I don't know what happened there. I don't know at all what's happening. Where it's just rigid transformations. So again, all cases meaning always true, some cases meaning sometimes true, no cases meaning never true. If two figures are similar this time, then they are congruent. Discuss 30 seconds. Sometimes, always, never. Ready, set, go. And time is up. Let's see how you did this time. Let's just take a vote. Let's go straight to vote. Who says it's always true? Hands up. Who says it's sometimes true? Hands up. Who says it's never true? Hands up. Good. 100% of you guys got it correct this time. It is sometimes true. It is true for some cases. Exactly. Sometimes true. Because here, if they're similar, then that means I maybe did a rotation and a reflection. And if all I did is a rotation and a reflection, would it be congruent? Yeah, because that's just rigid transformations. But maybe I did a translation and a dilation. Would that be congruent? No, because of that dilation. So sometimes it's going to be true, sometimes it's not going to be true. And here's the last one. I've drawn this little diagram to help make sense of it. If an angle is dilated, so I've drawn an angle, and it's going to be dilated, with this center, this vertex, being the center of dilation, the angle measure may change. Sometimes, always, never. Another 30-second discussion here. 30 seconds, ready, set, go. What's going to happen if I dilate that angle? It's going to change, right? Sometimes, always, never. I should be hearing more discussion than this. Okay, time's up. Let's take a vote again. We're just going to go straight to vote. If this angle is dilated using this vertex, the vertex of the angle as the center of dilation, the angle measure may change. Sometimes, nope, sorry, we'll start with always. Always, raise your hand if you say it's always going to change. Okay, raise your hand if you say it's sometimes going to change. Raise your hand if you say it's never going to change. And again, you guys, 100%, you guys weren't discussing, so I was concerned, but you weren't discussing because you knew it was so obvious. This is never going to be true because the angle is never going to change through a dilation. Never true because the angle measures don't change. Angle measures don't change in rigid transformations or in dilations. Hope you're writing this down. These are part of your notes. And understanding that is really important as we move on to our next exercise. Here we have two figures. We have a square and we have a rhombus. I'm not even going to read the directions yet. I'm just going to show you that this square, what are the lengths of each side? 2, 2, 2, 2. What about the rhombus? What are the lengths of each side in the rhombus? Also 2s. What are the angles in this square? 90 degrees, because it's a square, so by definition 90, but they are also marked for us. And what are the angle measures here in the rhombus? Okay, 120 and 160. Priya says these polygons are similar because their side lengths all have the same length. Claire says these polygons are not similar because the angles are different. Notice that they're both saying basically true statements. Priya is saying they have the same lengths. Do they have the same lengths? Yeah. Claire is saying they have different angle measures. Do they have different angle measures? So yeah, you now need to determine, are they similar or not? So do you agree with Priya or Claire? Explain your reasoning. 60 seconds to discuss. Ready, set, go. Finish up your discussions. Okay, let's come back together. Do you agree with Priya or Claire? I'm looking for hands up to share their discussion, to share their thoughts. I'll wait until I get some more hands. I heard some good discussions. I want to see those hands. I'll just keep waiting. Thank you, Parker. What do you think? Why do you think Claire is right? And why does that mean it's not similar? Okay, but is similarity dealing with just what they look like? Go back to the definition of similarity. Add to what Parker is saying and help him out, please, Mason. Okay. You agree with both? So they're both similar and not similar? No, because we have a very precise definition of similarity, we can easily say if it is or isn't. It can't be both at the same time. Zeta? Okay. I appreciate your thoughts, but again, I think that you're forgetting the definition of similarity. There is a very precise definition of similarity, and Zeta, I think you got lost in the real world idea of similarity and not the mathematical concept. Let's review that mathematical concept. Two figures are similar if one can be obtained from the other through a sequence of translations, reflections, rotations, dilations. If I translate an object, is the angle measure going to change? No. What if I reflect an object? Is the angle measure going to change? No. What if I rotate an object? Is the angle measure going to change? What about if I dilate an object? Is the angle measure going to change? You guys all told me right here that the answer was no. Remember how we wrote that down? Angle measures don't change in rigid transformations or dilation. So let's come back one more time. Eyes on the screen. Pencils down. Eyes on the screen. Two figures are similar if one can be obtained from the other through translations, reflections, rotations, dilations. If all I'm doing is translating the figure, is the angle measures, are they going to change? No. What if instead of a translation, what if I'm reflecting it? That means I'm just flipping it. Are the angle measures going to change? What if all I'm doing is rotating it? Are the angle measures going to change? What if I'm dilating it, making the figure bigger? Are the angle measures going to change? Once again, we said no right here. So, is it possible to take this figure to this one through translations, rotations, reflections, dilations? No. How do we know that it's not even possible? Because these are different angles. So we should be agreeing with Claire. Claire is the one who is right because these are not similar. We are writing this down. If the angles were the same, then we probably could say that they are similar. Correct. Claire is right because these are not similar since the angles changed. We need to remind ourselves, angles don't change in rigid transformations or dilations. Pencils are moving. If it is important enough for me to write down, it is definitely important enough for you to write down. Now let's try this again. Now we have these two figures. They are both rectangles because they have right angles. See them? Jada says, these rectangles are similar because all the side lengths differ by 2. Lynn says, these rectangles are similar. I can dilate, I'm going to color code as I read this, AD and BC by a scale factor of 2. Let's test that out. 2 times 2 is 4. And 2 times 2 is 4. True statement so far. And AB and CD using a scale factor of 1.5. Let's test that out. Here's CD. 4 times 1.5, what does it give you? It does give you 6. And here's the AB multiplied by the scale factor of 1.5 and we get 6. So those are true statements. So again, Lynn says these rectangles are similar because I can dilate the orange sides by a scale factor of 2 and the green sides by a scale factor of 1.5 to make the rectangles congruent. Then I can use a translation to line up the rectangles. Do you agree with Jada or Lynn? Explain your reasoning. You have 60 seconds. I need good discussion. I need good answers when we come back. 60 seconds, go. Make sure you're ready to answer who you agree with. 30 seconds left. Okay, who do you agree with? Thank you for these hands. I appreciate the engagement. Maddie, what do you think? She was very clear on this sequence of transformations, right? She mentioned the translation. She had our scale factor. Xander. Okay, why isn't it Jada? Which actually is correct. You need to make sure you understand what that means. Differ by 2. She's saying 4 plus 2 is 6. Should we be adding as we go through these? No. So is Jada's justification correct? It's mathematically accurate, but is it a correct statement to show similarity? No. So she did say something correct that we're differing by 2, but that's not how we prove similarity, right? We can't add. So that leads to, is Lynn really correct? The answer is no. We're going to go back to review our 7th grade material. These are from your Math 7, Lesson 4, and Lesson 5. These are talking about scaled copies, but scaled copies are just dilations. When a figure is a scaled copy, or a dilation, of another figure, we know that, make sure you're paying attention here, all distances in the copy can be found by multiplying the corresponding distances in the original figure by the same scale factor. How long is this right here? This is 2, right? 2 times 3 is 6. How long is this right here? 2. And 2 times 3 is 6. And what about this one? This was up 2 and over 1. Well, up 2 multiplied by 3 is up 6. And over 1 multiplied by 3 is over 3. So every distance was multiplied by the same scale factor. Let's see that down here where we also summarized. Distances or lengths in scaled copies, they're not the same, but they do change proportionally. If one side is multiplied by 3, then all sides need to be multiplied by 3. And did Lynn multiply the sides by the same number? No. The orange ones multiplied by 2 and the green ones multiplied by 1.5. So are these similar figures? Okay, let's write this down because nobody got this correct. Both students are incorrect. These are not similar figures. Pencils are moving. We're going to really explain what each person got wrong. Jada. Added 2 when only multiplication is allowed. Lynn is also wrong because Lynn changed the scale factor. Here's the big takeaway that you need to understand from this. When we're looking for similarity, we need to check the angles. The angles shouldn't change. But that's not the only thing we should be checking. We also need to check the side links. Check side links for the same scale factor. Meaning, if I'm multiplying by 2, 2 times 2 is 4, then I also should be multiplying by 2 here. 4 times 2 should have been 8 if these were scaled copies or dilations of one another or similar figures. Now is time for an activity. It says your teacher will give you a card. Find someone else in the room who has a card with a polygon that is similar but not congruent to yours. When you have found your partner, work with them to explain how you know that the two polygons are similar. For you online learners, this is going to look a little bit different. For you online learners, if you're working through Canvas, you are going to see in the Find Someone Similar activity, I have a PowerPoint that allows you to do it digitally. Just like we've seen in the past with these activities, you'll need to save it to your own drive, otherwise you won't even be able to make changes. So you'll just click on it. For me, I'll have to click it in incognito so that it doesn't start with me already logged in. And then you'll have a message that looks something like this. Read only, you don't have permission to edit this file. So we need to go File and download it. Download it to your own computer. Make sure you download a copy. Any of these other options will make it so it's not editable. So download a copy. It's going to download here. If you're on Mac, then it's going to download and it'll show somewhere up here. And now I've got this downloaded copy, which is then going to have to be enabled. You'll have to enable the editing so that you can do this. And you can just move on to the next page. Here's all of the figures. These are the same cards that each of the individual students in class have. But what you're going to be doing working online is you're just going to be pairing them up, finding ones that are similar. I'll do the first one for example. We can see rhombuses, another rhombus, rectangle, 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 rectangle. So since they're similar, we're obviously going to be pairing up the rectangles with the rectangles. We need to figure out exactly which rectangles would go together. These are all our rhombuses, so just kind of pairing each of those up. So I'm just kind of moving these things around. And then I've got my squares. And obviously these squares are going to be similar because they have all the same angles. And then we just need to figure out what the scale factor is. And honestly, if you're really thinking about it, how does a 7 change to an 8? I'm not sure, but however a 7 changes to an 8, this 7 is also going to change to an 8, and this 7 is also going to change to an 8. And the one thing that you need to understand is, if you don't know how to find the scale factor by going forwards, I don't know how a 7 changes to an 8, you can always work backwards. 8 divided by 7, and that will help you find that scale factor. Since you're working online and doing this digitally, you also have the advantage of doing those rigid transformations. For example, I can translate it so that those vertices line up. There's the translation piece. I can't get them to line up perfectly. But then you can also perform a dilation to show that they really truly are going to line up, just like I did there. So we can show that doing those transformations, I should say, will take one figure to the next, proving that they are similar, but you can also pretend like you're doing it just like the rest of the class and just try and find those matches. Okay, that's it. Once you have all of your matches made, then return to the video and we'll go over the answers. But pause the video long enough for you to do and form all of these matches here on the PowerPoint. And now that you've done that, let's take a look. Hopefully you paired up these rectangles. These are similar. Again, notice all of the angles are the same. They're all right angles. And we ask these questions like, how does an 8 change to a 12? Notice that I'm pairing up the long side with the long side and asking, how does that 8 change to a 12? Again, if you don't know how to work forwards, you would work backwards. 12 divided by 8 is equal to 1.5. So that tells me that I must be multiplying by 1.5. How does a 6 change to a 9? In order to show that they really truly are similar figures, we would hope that it's the same scale factor. 6 times 1.5 is equal to 9. And I'm not going to do that for every single side because this side 8 changed to a 12, this side 8 changed to a 12, so it's going to be the same process. The next ones that you should have paired were these two rectangles. Notice that this one might have been challenging because you did have to do the sequence of transformations that included a rotation. Because here the long side is 5 and it goes horizontally, but here the long side goes vertically. So there was a rotation that occurred. So how does this 3, the short side, change to be a 1.5, the short side? Again, if you don't know how to go forwards, go backwards. This is one that we can do mentally. The scale factor is 1/2. Same thing when I rotate, this long side rotates to this long side. And again, that scale factor is 1/2. Notice that all of the angles are the same. These are still rectangles, so that made it a little bit easier on that one. We already did this squares in our example. How does a 7 change to an 8? Again, if we don't know how to go forwards, we work backwards. 8 divided by 7 is 8/7. No need to change it to a decimal because it's a repeating decimal. So just know that we're multiplying by 8/7. And whatever I do to this 7, I'm doing to all of the other 7s. So all of these are multiplied by 8/7 to give us 8. These two would have been the ones that were paired together. Again, things that I'm noticing: 60-degree angle, 60-degree angle, 120-degree angle, and 120-degree angle. That should have automatically eliminated this one down here that was a 50-degree angle and a 130-degree angle, because with these different angle measures going from up top down here to this bottom one, you can see that they are not similar because they have different angle measures, and the angle measures should stay the same. This figure would have been reflected before being dilated. How does a 3.5 change to a 4.5? I don't know, so I would have worked backwards to find that scale factor. 4.5 divided by 3.5 is equal to the fraction 9/7. Whatever I'm doing to this 3.5, I'm doing to this one and this one and this one. We're multiplying each of those by 9/7. And down here, again, we have our same angle measures. This is another reflection. How does the 9 change to a 10? I don't know, so I would work backwards. 10 divided by 9, or 10/9. And whatever I'm doing to this 9, I would be doing to this 9 and this 9 and this 9, because they all change to 10. Now, we do have this "Are you ready for more?" It says, on the left is an equilateral triangle where dashed lines have been added, showing you can partition an equilateral triangle into smaller, similar triangles. Find a way to do this for the figure on the right, partitioning this figure into smaller figures that are the same shape. Pause the video, see if you can find ways to do that, and then we'll return with the answer. The best way to do this, and the one that will produce the fewest number of pieces, is to just start by turning that into that sort of L shape right here. You can see that L shape forming right here, and then I would have to repeat, I want that same L shape here. See that? And the same L shape here. And we've got that same L shape there. These are each going to be similar because the scale factor is 1/2. Notice that this side length here is 4, and the side length in the new figure is 2. The 4 changes to a 2 by multiplying by 1/2. And now let's move on to our summary. When two polygons are similar, every angle and side in one polygon has a corresponding part in the other polygon. All pairs of corresponding angles have the same measure, and corresponding sides are related by a single scale factor. That's important to note because that's a mistake that was made in class. Single scale factor. Each side length in one figure is multiplied by that scale factor to get the corresponding side length in the other figure. Consider these two rectangles shown. Are they similar? We might be tempted to say yes because they are both rectangles. However, if we look really close, we can see that we've got to pay attention to the side lengths. Yes, they all have those same right angles because they are rectangles, right? So the same angles. However, let's pay attention to those sides. And I'm actually going to work backwards, different than what it shows here. How does a 2 change to a 3? That's something I can do mentally. If not, always work backwards. A 2 changes to a 3 by multiplying by 1.5. I would hope that I can multiply by 1.5 here to show that they're similar, but 3 times 1.5 actually gives me 4.5, not 4, because what I'm multiplying by here is 1.3 repeating. So, since I am not multiplying by the same number, these rectangles are not similar. The scale factors must be the same, and they are not. We can also see in these two figures that these are not similar because the angles are different. Here I have a right angle because it's a rectangle, and here I have non-right angle, so it is a parallelogram, but the angles changing tells us that these are not similar figures. So the grand takeaway from all of this is, in order to check for similarity, we need to check for two things. We need to check the angles. The angles shouldn't be changing. And we also want to check the side lengths for a single scale factor. So check the side lengths for a single scale factor. And now it's time for our cool down. Are these two figures similar? Explain how we know. First of all, I'm seeing a 55-degree angle, and look at that, a 55-degree angle. That's encouraging. 55-degree angle, 55-degree angle, 125-degree angle, 125-degree angle, so that's all great. Our angles are the same, so I did the first step, I checked the angles. Now we need to check the side lengths for a similar, or the same scale factor. How does a 4 change to a 3? How does the 4 change to a 3? And I don't know, so I would work backwards and go 3 divided by 4, which is equal to the decimal 0.75. How does a 6 change to a 4.5? And I don't know, so I would work backwards. 4.5 divided by 6 is, lo and behold, it's that same 0.75. So these do also have the same scale factor. Your practice problems are the Lesson 7 practice problems, so make sure you complete those. That's it for today. Thanks for watching. We'll see you next time.